I'm going to introduce two different things, which today are going to seem not very connected, or maybe not as connected as they could be. I'm going to define the induced metric of the surface and talk about that for a bit. And then I'll talk about geodesics and length minimizing curves. And I'll just leave those two topics as separate for today. I want to introduce them both. And Justin will do his lecture on discretizations of geodesics on Wednesday. And then next time, I'll bring the two topics together when we talk about covariant derivatives. In case I'm going to talk about next time, I'll bring these two topics together. So, yeah, so don't worry about not being able to connect parts 1 and part 2 of the lecture yet today, because I'm not making that connection explicitly. Do that next week. So that's the outline. Okay, so here's some pictures. I just want to go through this slide. The point really is to show you these pictures here. Okay. Okay. So I want to give us some intuition for what the second fundamental form is saying. So let's take a simple surface. Let's take a graph of a function. Okay. And here I'm saying without loss of generality, I can assume that f vanishes to first order at the origin. What this means is both f is 0 as well as its derivatives, or the first two derivatives. I mean, df by dx at 0 is equal to 0, and df by dy at 0, 0 is equal to 0. And of course, f itself is equal to 0 at the origin. So to first order means 0 up to and including the first derivatives. Okay? So I'm saying without loss of generality, if we want to understand the surfaces in general, because of the homework problem that you have on homework 2, which is to show that any surface can be locally represented as the graph of as a graph of some function over its tangent at any point. So to unpack that statement, in other words, the statement of your homework assignment, let's just draw a picture of it. So I don't know. Here's your average hyperboloid of one sheet, right? So this is just any surface you like. Well, let's just pick a hyperboloid for good measure. Let's pick a point somewhere on the surface, maybe not there, maybe just right next door. This is a point P on the surface, and you draw. Oh, maybe this is bad actually. Let's go right on the edge. So what you do is you draw a tangent plane at the point P, and then what you want to do is rotate. So in your mind, you're rotating and translating so that P goes to the origin. This is the point P right here. And the plane goes to the XY plane. So just take this entire setup and rotate it sideways. So it's going to look like this, and here, right? And the point P is somewhere like this, and here's the plane, and let me just draw the axes in a different color. Here's the z-axis, here's the y-axis, and here's the x-axis, right? And there's the origin. Okay? So the idea of representing a surface as the graph over its tangent plane is this idea. You pick a point, you pick a tangent plane, you rotate the whole thing such that it coincides with your XYZ picture. And then what you do is you forget about everything else. You sort of locally look in here. So what you get then is just the plane and the axes. The axes, and then the surface is something. I guess it's going to look sort of like well, sorry. I shouldn't try to draw it too accurately, but it certainly is going to go through the origin. It's going to be some kind of something like this. What do you call this thing? Saddle surface, some kind of a saddle surface that touches the origin and is flat at the origin, because remember, after all, these things relate to the tangent vectors at the origin. Okay? So your homework assignment was designed to walk you through the 5 different steps which go from a general surface to expressing that general surface in this special form where there's a function f, a graphing function involved. And really the surface, after you rotate it like this, is just a graph of that function. Okay? So this is the big picture behind your homework assignment. Anyway, I'm saying that I want to study the local shape of a surface using the second fundamental form. So let me just go ahead and take my surface and put it into this nice standard form. So the standard form means represented as a graph over the tangent, over the xy plane, where the graphing function vanishes to first order. Okay, so the graphing function vanishes to first order, right? I should make a change here, sorry. I changed my control settings to this stupid thing to go to sleep. I don't want to do that. Okay, we'll do that. All right, good. Okay, we're back. Okay, so the idea is we can represent the surface in the standard form, and once we have the surface in the standard form, well, you can express the second fundamental form in a really simple way, right? In fact, on your homework assignment, you worked out the second fundamental form for a graph, and it didn't look like this, right? It had an extra denominator term in it with the square root of 1 plus the gradient of f squared, right? So the second fundamental form of a graph doesn't look like this. What it has, though, is it looks like that, plus a bunch of first derivative terms. And those first derivative terms, when you go to the origin of this nice coordinate system, they go away. Okay? So without loss of generality, the second fundamental form at that point looks exactly like the Hessian matrix. So it was a second matrix of second derivatives. So elsewhere, when you move away from the origin, this nice form is no longer true. Those extra terms come back. But at the origin, those terms vanish. So you just have this nice system. So bottom line is, once you get to here, it is sufficient to understand the nature of the Hessian matrix if you want to understand what the second fundamental form is doing at a point. Really locally. Okay, so now the fact is we have a quadratic form. How do you understand a quadratic form? You look at its eigenvalues. Okay, the eigendirections are orthogonal, and the eigenvalues, well, you have 2 of them. They can either be both positive or both negative. You can have one of each sign, or some of them can vanish, or they can both be equal. And if they're both equal, they're either equal positive or equal negative. Okay, so the pictures that I'm drawing for you here, or I've shown you here, represent the first 3 cases. So your typical elliptic point, the origin is an elliptic point, that special point you chose and translated and rotated and so on, put in the origin, is an elliptic point if both the eigenvalues are either positive or negative. And in that case, it looks like this. So it's bowl-shaped. Positive means the bowl points up, negative means it points down, but still, so intrinsically it's a bowl. Right? Hyperbolic region looks like this, one of each, one eigenvalue of each sign, and that's in fact what happens on this hyperboloid with one sheet. Right? You have the equator here is rounded inwards, and this transverse direction is rounded in the opposite direction. So you have a negative eigenvalue one way, a positive in the other way. A parabolic surface, a parabolic point, is one direction is 0. So a parabolic point can look like this. Here you have a positive direction, and then along the valley of this parabolic or parabolic surface, you have the 0 direction. And the planar point can look like a plane because it can be completely flat. And then an umbilic point, what's an umbilic point? Well, both are equal. That just means, well, this picture applies, or I guess the flat picture, planar picture applies. But the fact that both are equal, that just, the complication there is that, remember we were going to say that the eigenvectors form a basis, a unique, geometrically well-defined basis. Well, that's only true if you can distinguish one from the other. And if you have 2 eigenvalues that are equal, you can't distinguish which vector is which. So that's the only special thing you need to know about umbilic points is that the basis is well-defined. Okay, so, right, so this is the definition of points. Now, how would you prove, the question for you guys, how would you prove that this behavior, these three behaviors, results in pictures more or less like this? How would you prove such a thing? And remember, I'm not trying to describe the surface as a whole, I'm just trying to describe a small neighborhood around that specially chosen point. How would you prove such a thing? If you know a function and its two derivatives at a point, what can you make some statements about the function in more general terms? And what's the name of that theorem? It begins with a T, ends with an R. Yeah, that's right. Okay, so you have Taylor's theorem, which says you can do a Taylor expansion of the graphing function in the origin. The function value is 0. The derivatives are 0 as well. So the first term, the most dominant term in the Taylor series is this guy here. So what that means is, and the second order term, the next order term is cubic, and it's small, right? It's insignificant in comparison to that one. So what that means is locally near a point, as long as the eigenvalues aren't, none of the eigenvalues are 0, that means locally near a point the second derivatives tell the whole story. And that means the surface looks like, looks locally, in fact, like this, or upside down. But it looks like a quadratic surface. It looks like the graph of a quadratic function. And there's only really two kinds of graphs of quadratic functions out there. There's paraboloid, elliptic with elliptical cross-section or whatever, and then there are these saddle surfaces. So the Taylor theorem tells you that if your second fundamental form is of one of these two kinds, then your surface looks like this, either this or this, locally. Later, elsewhere, it could do other things, but locally, that's the way it is. Okay, what happens? What's the complication in Taylor's theorem when one of the eigenvalues is 0? Someone know what goes wrong? What can go wrong with Taylor's theorem when the eigenvalues is 0? Think about your Taylor's expansion in one variable. Right? Think about the Taylor's expansion in one variable. This is already gone. This is already gone. So the Taylor's expansion really starts here. And if this is gone, well, what you have to do is go to the next term in the Taylor series to understand the nature of the surface, right? So in this case, if the next term happens to be cubic, then you know your function looks like a cubic, right? If the next term is quartic, then it looks like this. It's sort of extra flat in the middle. Well, in my setup, I don't know anything about the third derivatives of the surface. Right? I've just told you the first and second derivatives and zeroth derivative. So in the case of 0 eigenvalue, that means your Taylor's theorem is inconclusive because you would have to go to the next order, but I haven't told you any information about the next order at all. And so that's why you can't actually say that the surface looks like this. It could look like something different. What's an example of where it could potentially look different? How might this look? Okay, so this here is supposed to represent one 0 eigenvalue and the other non-zero. So here's my non-zero eigenvalue direction, and here's my 0 eigenvalue direction. What could possibly happen that it make it look different from this? You need to have quadratic behavior pointing up in one direction, but you have inconclusive behavior in the other direction. So what could the shape of the surface look like? Yeah, you could have some, so both are possible actually. So you could have cubic behavior, right? You could have it being very flat right in the middle, but then sort of tipping off downward over here, and then pulling upward over here. You could have that. Or in fact, you could have what Hardik said, which is you could have it being parabolic, like shaped. You could have it going up all around, except it's quadratic in this direction and quartic in this direction. So it's like too flat to be measurable by the second fundamental form. right? It still goes up all the way around, but the second fundamental form doesn't measure because the function looks like super flat in the middle, right? This is the graph of y equals x to the fourth, right? It's very flat in the middle. So the second derivatives don't give that information. Yeah, Trent?
When we've already made this kind of linearization approximation, how concerned are we about these higher order terms?
Well, you're not. You can't be. Yeah, you can't be. Yeah. So usually this stuff is valid for analysis when you then also have a step where you show the thing is non-degenerate, no zero eigenvalues. Yeah. So really the most important pictures are these, and then if you don't have this, then you have to do more analysis, blah, blah, blah. Okay, so this is the intuition I wanted to give you for what the second fundamental form says about a surface, what it doesn't say. Okay, so one important formula that we had from, so this is the next slide. I want to give another interpretation of curvature. In fact, this time the mean curvature. Justin actually used a formula like this. I think in the interest of time, I'm not going to go through the derivation. I'll put it on the internet. I'll put it on our course webpage as a supplement. And you can see the derivation. It's kind of neat. Well, in fact, there's one cool formula which not everybody knows, but then there's another place where you do some standard calculations involving the product rule as usual, and out comes the result. But let me just pull you through the important parts of this slide and leave the derivation for the supplement. Okay, what Justin used in his last lecture was that the mean curvature represents the gradient of surface area. So this is a bit of a difficult concept to swallow, but it's important to do so because it'll come back again, in fact, in a few minutes. So the surface area is an operation on a surface, right? So you give it's functional, let's say. It's an operation where you give the input as a surface and the output is a real number, which is the area of the surface. So this is kind of a weird object, right? So how do you compute a gradient of that? What does it mean to be the gradient of the area? Think about that for a second. So what you have is the input is surface, the output is area of S, which is a positive real number. So how do you compute the gradient of this kind of a thing? Well, what you need to do is differentiate. Gradient when you take a derivative, right? You need to differentiate this thing as the input varies. So what you need is a variation of the surface. Call it S epsilon, and then you want to compute d by the epsilon of area of S epsilon at epsilon equals to 0. And this is somehow the gradient. Okay, well, I'll make this, well, we'll see this more precisely in a second, but anyway, this is the idea. You have this operation on surfaces which produces a real number. How do you find its gradient? You vary, you differentiate in a variation of the input. So, how do I do a variation of the input? So how do I vary the input? Okay, well that's actually pretty straightforward, because you can think about it in geometric terms. Here's my surface S, and what I would like to do is deform S. My S epsilon is going to be a deformed version of S. So think of S epsilon as a, change the picture just a bit so it's easier for me to draw. Think of S epsilon as a slightly deformed version of S. There's S. And I want to think of S epsilon as some sort of very nearby deformation of S. Okay? So S epsilon is just a small change in the surface. This is what it means for a surface to vary. Okay? Now, I want to write this variation down in a way in which I can compute with it. I want to get my hands on what it means to be a variation. So what you do is, at every point you find the normal vector, right? And if you walk forward, here's P, here's the normal vector at P. If you walk forward in the normal direction, eventually you're going to hit the target surface. I mean the variation, the varied surface. Right? You start at the unvaried surface, you walk forward in the normal direction, you eventually hit the varied surface. Okay? So let's say that at P, I have a normal direction n of P, and the height of the varied surface over the unvaried surface is going to be a function f of P. Okay? So that's the picture of this, well, almost, this situation here. Okay? So all I've thrown in is an extra parameterization, but never mind. Think of this as, this phi is a point on S. This phi epsilon is a point on the varied surface. So a point on the varied surface equals a point on the old surface plus an amount epsilon times f times n in the direction of the normal vector at the point. So maybe I need to throw one more thing here, which is I want to put an epsilon here. I want it to be a small variation, small little variation. Okay? So that's this. Does that make sense? Okay. So what I have to do, so if I want to do calculations, I want to compute this thing, I've got to take this formula for the nearby surface and plug it into the surface area. Okay? Right, so what's the surface area? Well, remember, it's the integral over the coordinate patch of this thing. This thing was the determinant of this matrix. This d phi epsilon transpose d phi epsilon. Right? It was the determinant of that the area of the it was the area of the little coordinate rectangle pushed forward. Okay, so my job now, in order to find the gradient of the area, is to do this derivative. So let me not tell you how the derivative, how it's done. Save that for the supplement. This way you can ponder it just in your own time. But let's say going from here to here involves a neat formula about differential determinants. The derivative of a determinant of a matrix equals the trace of m inverse times the derivative of m. Do you know this formula? Yeah, I'll write this down in something. Anyway, there's a neat formula which is just purely nothing to do with geometry, linear algebra, about the derivative of a determinant. Out comes the trace. Anyway, so what you do is you use that neat formula to bring this derivative operator onto the inside, onto this matrix. You have to differentiate this matrix. And it turns out when you differentiate that matrix, what comes out are, well, there's a trace, right? So you get the trace of the second fundamental form, which is the mean curvature. So I'll show you, you'll see tonight, if you look online, you'll see this derivation. But let's just go to the very end. The gradient of the area, the variation of the area, equals the integral of the mean curvature over the surface. And of course, times the function f, which sort of adjusts for how the variation is changing, right? But it's the mean curvature that controls the variation. Okay, how do you make that integral as small as possible? I want to make the area decrease as fast as possible. How do I make that integral as small as possible? Well, I choose f to be very large, of course. But suppose I have to make f sort of norm 1. What's the best f I can choose to make that thing as small as possible? Okay, so if this is a gradient, and here's an average direction in which you want to walk, and I want to make the function value as small as possible, how do I walk? Do I walk like that? Do I walk away from my gradient? Or do I walk in the direction of the gradient? Direction of the gradient. Okay, so why does that happen? Well, it's because when you do this, you get squared, right? Things square up and it's positive. Same here. I'm integrating my deformation, which can do anything it wants, against the mean curvature. How do I ensure that everything is as positive as can be? Well, I make the deformation be the mean curvature. So if the mean curvature is big and positive, I want to walk with big values. If the mean curvature is negative, I want to walk backwards, right? So I use the mean curvature to reduce the area. And in fact, you can see that kind of over here, right? Because the mean curvature points inwards, right? Points inwards. And if I want to reduce the surface area of this bowl, intuitively, what do I have to do? I have to flatten the bowl out, right? To flatten it out. So that means walking upwards and flattening, pushing it up. Here, well, we don't know what the mean curvature is, but there's a positive curvature direction like this, and in the opposite direction is a negative curvature. So you could well imagine that the mean curvature here is 0, right? seems reasonable. One is positive, one is negative. They look kind of the same, so maybe they cancel. And sure enough, this is a minimal surface, or at least could be a piece of a minimal surface, which is a surface whose area is already as small as can be. It's like a soap bubble or a Pringle chip. The area is as small as it can be. So moving in any direction whatsoever is not going to help you. So mean curvature equals 0, leave the surface alone. Okay, so there's my interpretation, and I'll show you these two steps in a supplement later on. Yeah, Michael?
Quick question. So is it clear that your deformed surface is in fact a surface according to the definition?
Yes, it is. I think. Probably when epsilon is sufficiently small and f is not f and its first derivative are sufficiently small in pointwise norm, probably. Because this is a parameterization of the nearby surface. And I'm pretty sure that if I check the determinant of, this number here, if that determinant is non-zero, it's a regular surface. I'm pretty sure that the determinant of this is very close to the determinant of the original parameterization, which means it's probably not zero. It's not going to be zero, unless epsilon is large or f is somehow badly behaved. But other than that, this will be a surface, because there's a parameterization for it. Okay, so that's the end of the first, this is the end of the recap, or the completion of last week's lecture. Okay, so now we're going to move to the second of three somewhat disjointed topics in this lecture, which will all be unified next week. Well, you're not 100% disjointed, but anyway, I'll define 3D induced metric and talk a little bit about it. So let me erase, and if you guys have any questions on previous material, you can ask, and then we'll keep going. Okay, any questions on previous stuff? Okay, so my way of smoothly transitioning into this section was to make this first observation up here, which is if you have a parameterization of a surface, right? So here's my surface, here's my coordinate chart, neighborhood U, phi maps to the surface, right? This quantity d phi transpose d phi has actually shown up several times already. It showed up on the last slide because it was the area element. It showed up when we talked about parameterizations and the fact that parameterizations have to be one-to-one. The determinant of this thing has to be non-zero. And actually we also computed, or this thing also showed up when we found the unit normal vector of a surface, right? We took E1, we took the coordinate vectors and did their cross product, and then had to divide by the length of the cross product. And this thing showed up in the length of the cross product. So this quantity seems to show up all over the place. So what's it all about? Let's give it a name. Let's call it G. And G is a matrix. So G is a matrix. And it's in R2 by 2. It's a 2 by 2 matrix. Because phi is 3 by 2, right? So when you do this, you get a 2 by 2 matrix. Okay, so what is it? Well, it's got a name. It's called the induced metric. So let me walk you through this, set of bullets here. So just to remind you of all the various things. So, right, so first of all, okay, yeah, so I guess this thing is easy to understand once you are reminded of all the various pieces. So let's call this the coordinate vector E1. Let's call this the coordinate vector E2. So of course, E1 is this, 1, 0, and E2 is 0, 1. All right, so just a standard basis, but in the parameter plane. And these things get mapped forward to two other vectors. So this is phi at the origin, and this is d phi 0 at E1, and this is going to be d phi 0 at E2, or acting on E2. So you get two other vectors, and let's call this one capital E2, and let's call this one capital E1. Okay. So yeah, so this is when you have a parameterization. This is what you get tangent vectors to the surface. the surface S. Okay, right, so this is the setup. Just observe that EI is equal to the matrix d phi at 0 acting on EI, which is simply d phi by d UI. So it's that thing. At 0, of course. Okay, right. So now let's look at the inner products of these vectors. So before when we drew this picture before, what I did was I took this coordinate rectangle and it moved forward to some sort of wedge of vector, some sort of narrow wedge of vector, whatever, depending on different angles, whatever. We looked at the entire rectangle as it moved forward. But now I just want to look at the geometry in a slightly different way. I want to look at the two vectors separately. And then I want to look at their lengths, how the lengths change, and I also want to look at the inner product, how it changes. Okay. So so in other words, I'm looking at EI inner product EJ. So this is summation d phi by dui, d phi by duj, and then I have an index up here, and the k index runs from 1 to 3. So this here is an expression for the inner product of the two basis vectors. And of course, the length of EI squared is just the inner product of EI with itself. So I'm looking at lengths. I'm looking at lengths and inner products. Okay? All right. Well, this is something special, right? This is in fact, right here, this is in fact the ijth component of d phi transpose d phi. Right, this is an inner product of vectors. Right, inner product of the d phi by dui vector with the d phi by duj vector. How do you see it? It's a family of inner products, one for each I and j, right? So how do you get that all in one? You get that all in one by taking a matrix whose columns are these whose columns are these d phis, and the set of all inner products is matrix transpose times the matrix. Did everyone see that? Okay. So what I'm saying here is that the induced metric of a surface, this object G up here, is really the Euclidean inner product. It's really just the inner product of tangent vectors. Nothing more than the inner product. But it's not the inner product as it lives up here, because that's so trivial. That's the Euclidean inner product. It lives up here. It's ordinary inner product, dot product of vectors. You know how to do that. It's not the inner product that lives up here. It's pulled back, and it lives in the coordinate plane, in the parameter plane. So it's the pullback of the inner product, the Euclidean inner product, but the inner product of tangent vectors. So that's what I mean by restriction to the tangent plane. It's the inner product of tangent vectors pulled back into the parameter chart, the coordinate chart, or the parameter. Okay, so what I'm saying here is that whenever you have a parameterization, you get a representation of this induced metric as a matrix of coefficients. So you pull back the inner products, you get a matrix of coefficients, and that matrix of coefficients represents the inner product upstairs in a parameter plane. So this should have been induced, I guess. Okay, so that's the idea here, is that this object represents the inner product, but in the coordinate plane. It's actually a 2-0 tensor, but never mind tensors. We'll talk about tensors later on. For now, I'll just think of it as a matrix. Okay, does my definition make sense? Sound good, the definition? Okay, so now I want to spend just 2 slides talking about this idea of covariance. So remember, we computed a number of scalar quantities, like the surface area, the arc length, we computed these things, and I called them geometric. So the arc length is a geometric thing, which depends only on the shape of the curve. And the way we verified that is, well, okay, you had to define it using a parameterization, but then you verified that the thing was independent of the parameterization. So in other words, you check that your scalar quantity computed with respect to every parameterization you like is always the same. That's the idea of covariance for a scalar quantity, or being geometric for a scalar quantity. Well, a different property, which I'll explain in a second, holds for vector or tensor quantities. So I want to argue that this induced metric, because it comes from something geometric in the outside world, but it's only pulled back to the parameter plane, I want to say it's still geometric. But I can't use the rule that the scalar quantity that it should be unchanged when you do it in two different ways using two different parameterizations. I can't use that rule. Okay, the reason I can't. Right. So let me just emphasize this again. Right here. Sorry, let me just say what I just said again. I could imagine doing this in two different ways, right? I have my surface over here. Here's my surface. And then I have a parameterization here, another parameterization over there. I have my parameter domain here, let's call it U, and I have my parameter domain, let's call it V. And what I get is, I get Gij, which is the inner product of d phi dui with d phi duj. And over here I get, I don't know, let's call it G prime ij, which is d phi prime dui dvi, and then d phi prime dvj. So in differential geometry, you worry about this kind of stuff. Look, we have one surface, but we have two different ways of writing down the inner product. Which one's right? Well, the answer is they're both right. In the world of scalar quantities, you say which one's right? Well, you say they're only right if they're the same. But in the world of vector quantities, things are allowed to change. But they have to change in just the right way. So this is how you say they're both right. You have to verify that when you change basis, everything is okay. Right? The reason they're potentially different is because the basis used to represent them from one side to the other can also possibly change. So what you have to do is verify that you have the right transformations hold for passing from one set of components to the other. Okay? And this is the idea that different geometry is known as covariance. So the covariance of scalar quantities is easy. It's got to be the same all the time. When you start to deal with vector quantities, they have to be covariant. And covariant means satisfies the right transformation formulas when you change parameterizations. So let me give you an example of that. Walk through this slide here. Okay, maybe it's best to do it over here, right? So what you have is you have the E's here, E1, E2, and let's say we have F's over here, F1, F2. When you map this forward, you go to the same point. You get capital E1 and capital E2, and maybe you get a different basis. You get capital F1 and you get capital F2 there. Okay, so now it should stand to reason why the numbers should be allowed to be different, right? Because after all, let's say G11 or G12 is the inner product of E1 with E2, and G prime 1, 2 is the inner product of the red vectors. And the red vectors are different from the blue vectors, so why on earth should those numbers be the same? Does that make sense? What should work is that if you do a linear transformation from the red vectors to the blue vectors, then these components transform in the right way. So here's how you do that. Well, you use the chain rule, as always. So what I want to do is represent the F's as a matrix multiplication of the E's. So here's the definition of the F's. So this is psi, so phi prime. So it's the derivative of the second with respect to VI, the second parameter with respect to VI. You do this magic, which involves the chain rule, and out at the end of the day, you express the F's in terms of a matrix acting on the e's. And this is this famous change of basis matrix. It's the change of basis, change from the u variables to the v variables. Okay? So I can draw the picture. Maybe let me change this to psi so it coincides with the picture. Psi there, and put psi here as well. Okay? So in between, I have need to go the other way around, I guess. Need to go psi first, phi inverse. Not exactly what I have written there, is it? Okay, I suspect there might be a typo on the slide, which would suck. Yeah, I feel there's a typo on this slide. But okay, never mind, I'll check it later. In any case, what I want to say is that I express the f's as a matrix multiplication using a change of basis matrix with a change of variables matrix against the e's, and then I plug that into the formula for the inner product. Here's my g prime, here's this quantity, g prime, and I say that this g prime, plug in my change of basis, I pull out the stuff, and I get some operations on the of this change of basis matrix acting on the g. Right. So a formula like this is what it means to be covariant. So the components of the induced metric change covariantly if, when you change bases, or when you change parameterization and then you change bases, you get the change of basis matrices multiplied in here, like this. Okay? So this is what it means to be covariant in the case of vector tensor quantities. You got to have this matrix of the changes the components come into play in the right way. So again, this covariance computation, I just want to show you what it is. We won't do it every single time anymore. Although in principle, whenever you define a vectorial quantity using a parameterization, you always have to check that it's covariant. Just like when you define a scalar quantity like the arc length with a parameterization, you have to check that it doesn't change when you change the parameterization. Okay? So this is always a similar ingredient in these kinds of calculations. But we'll stop with that there. Okay, so what I've done, so the next topic is the third topic. So what I've done here is just introduced and hopefully demystified this quantity which has appeared several times. Okay, next time I'll spend an awful lot of, I'll spend the entire lecture talking about this quantity here and what it means for you. In fact, the next couple lectures are going to talk about this. Next two lectures of mine are going to talk about the intrinsic geometry, which is all contained inside this G, inside this inner product. Okay. All right, so that's the end of this little introduction to the metric tensor and covariance. We'll stop there. The next topic is to talk about geodesics. So let me erase, and then I'll ask a question. If you have any questions, you can ask. Maybe I'll leave that. Okay, any questions on that last section? Okay.
Is there any motivation behind restricting the covariance metric to being a linear transformation, or just because it's simple and it's position?
Well, let's say everything operates at the level of the tangent plane, and so some of the essence of this part of differential geometry is to use linear algebra as much as possible, right? So you try to express all these geometric quantities in terms of the tangent plane or variations of the tangent plane. So yeah, this is first order information about the surface. So all we care about is the local linear algebraic properties of things. So, right, so I'm going to talk about geodesics now for the rest of the lecture. Justin will talk also about geodesics. In fact, we're going to compute geodesics, or he's going to show you how geodesics are computed on a mesh surface. The interesting fact is that these geodesic computations were really only figured out like within the past 10, 15 years. That's very interesting. This has been around for like since the beginnings of differential geometry, 150 years. But computing them has only been around for like 10. That's kind of cool. Okay. How does this connect to the induced metric? Well, it turns out that this is intrinsic geometry, and I'm going to show you tomorrow or next Monday how this exactly does involve the induced metric. The point is, all that we do today involves only the induced metric and not the second fundamental form. That's what makes it intrinsic to the surface. You don't need the outside world. The second fundamental form has to do with normal vectors and variation of the normal vector, how the surface is shaped in the outside world, and so on. You don't need to know that to compute lengths on a surface. You just need to know the induced metric. The first hint of that is that the induced metric is actually on the board somewhere, on the projector somewhere already. Where is it? On this slide somewhere is G, although it isn't written as G. Actually, no, it's not. It's not this one. You're close, but it's not this one. V is tangential. K may not be. K is a vector out in space. Right? And remember, the metric is the inner product restricted to the tangent plane. So you're only allowed to plug in two different tangent vectors. So actually, not here, but it's close. So you're close. Where is it? Where does the induced metric appear in this overhead? Say again?
The variation
here? Here. Sorry.
D by D epsilon, right?
This one.
Variation is just the length of the curve, right?
Okay, so yes, the length of the curve. This right here. This right there. This is really equal to the inner product of the tangent of the curve by itself. And of course, here's the surface, S, and here's gamma, and here's a small variation, here's gamma epsilon. But the fact of the matter is, gamma dot epsilon is tangent. It's tangent to S. So this really is an intrinsic inner product. It's the inner product of tangent vectors. So the length of a curve is written in terms of the induced metric only. So that's the hint that this is going to involve the metric in more complicated ways than is apparent on this first slide. But what I'll do for the next couple of slides is I won't talk about that at all. I'll wait until Monday, next week. I want to introduce a different aspect of this right now. Okay, right. So let's walk through this slide here. So the question is, if I have a surface S, what is the shortest path? And I give you 2 points. What is the shortest path between those 2 points, P and Q, where the path is forced to remain on the surface? So simple, let's consider the sphere. Here's P, here's Q. The shortest path in space is, of course, a straight line between P and Q. But I'm not interested in that. I'm interested in the shortest path, which is an arc, some kind of arc, gamma, which lies on the surface. So here's my sphere as my S2. So I want to know what is the shortest path connecting P and Q on the surface. So that's the question which motivates the next couple slides. Okay, so we don't know how to answer this just yet, except maybe we have sort of an idea that, in the case of the sphere, it should be the great circle, right? So it's some kind of path, and you kind of figure there is one, right? Because you can draw all sorts of different paths between points, and you sort of keep looking until you find the shortest one. Or if you have one path, you can sort of push it in a short direction, and sort of tighten up the line. And you sort of figure there is one. by some kind of variational principle. There probably is one. Okay, but let's try to learn a bit more. So how do you do this? Well, okay, we don't know if there exists a shortest path, but let's suppose there is a shortest path, and let's find an equation for it. This is the standard approach, or the standard philosophy behind calculus of variations. What you do is, you assume you have the shortest path, gamma, and we make a variation of that path. Okay, so here's my picture of my variation. So let me erase the variation and redraw it. Here's the blue curve is gamma, and it connects P with Q, and my variation is going to be an endpoint fixed variation. So here's gamma epsilon. So it's going to be a small deviation of the curve gamma, and I still want it to connect to two endpoints. Did I say that? No, I didn't say that. It should still connect to the same endpoints. Okay, right. Now, length of the varied curve. What do we know about the length of the varied curve? Well, if the unvaried curve is a minimum, then the length of the varied curve is longer than the length of the unvaried curve, right? But furthermore, the length of that unvaried curve is really a genuine minimum. So if you're at the minimum of, so this is a function in epsilon, and when epsilon equals 0, you're at the bottom, right? As soon as you change epsilon, the curve gets longer. So this number, length of the curve, gets bigger, right? So you're really at the bottom. If you're at the bottom, you're a local minimum. That means the derivative is 0, right? So in these calculus of variations calculations, the left-hand side is 0 because you're always at a minimum, right? So the equation always starts the same way. 0 is equal to the derivative of the length in terms of the variation, and now you have to work it out. Okay? All right, so the integral you have to work out is the derivative of the length integral. And this is something we have to do in your homework assignment. Okay? You remember from your homework assignment that the answer, this answer is, after you integrate by parts and do some magic, right? The answer is you get the curvature vector of the curve. Right? It's the inner product of the curvature vector with the variation vector field. So what's the variation vector field? It's the vector field which creates this variation, right? It's the vector field V which creates the variation. So you move gamma in the V direction, you get gamma epsilon. For epsilon times the V direction, you get gamma epsilon. So V, in this particular case, is a tangent vector field. So V is tangent to S, which is what keeps gamma epsilon inside S for all, well, it's required, I guess. I guess that's the implication for all epsilon. So the fact that your variation moves inside the surface and doesn't leave the surface means the vector field that generates the variation has to be tangential to the surface. Yeah, great.
So the curvature vector here, is it the curvature vector that is on the surface?
No.
It's just the curvature.
Yeah, it's the curvature vector of the curve.
Okay.
Right, so I'm running out of colors. How do I draw that? Well, let me redraw the picture. Here's my thing, here's my surface, here's my curve gamma. Right? This vector, this curvature vector is your geodesic curvature vector that we saw in lecture 1. If gamma is parameterized by arc length, then it's perpendicular to the curve, and it may point out of, it may actually point out of S, right? This curvature vector is a thing associated to the curve. It's not associated to the surface, a priori. It's associated to the curve. Okay, so it's the geodesic curvature vector from lecture number 1. Okay, what's the equation saying? Well, the equation is saying this 0 equals the derivative and worked out is saying this here. It's saying that the curvature vector is orthogonal to every possible variation in the surface. Right? What this means is the curvature vector itself is orthogonal to the surface. Right? So, so the result, theorem, I guess, to be proved is that if gamma is shortest, blah, 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 in S, you know, connecting P and Q and all that, is shortest in S, then its curvature vector is orthogonal to the surface along gamma. That's the theorem we just proved, this one right here. Okay? So the curvature vector could have pointed in an arbitrary way, but if gamma is the straightest possible, if gamma is one of the shortest possible curves, then the curvature vector is normal to the surface. Okay? Right. That make sense? Okay, so now I need to make a definition, last thing I'm doing here. So I started off by asking the question, what is the shortest path? Well, I don't know if there exists a shortest path, but I derived an equation for it, which is here. And again, I still don't know everything. I don't know that if I have a curve that solves the equation, I don't know if it is a shortest path. All I know is there's a relation between shortest paths and that equation. Okay, I haven't made a relation sort of if and only if yet. It's not, there's sort of gaps in either direction. So that's why I'm going to make this definition, which is slightly weaker than what I want. I want to say, you know, I'd like to say every curve which satisfies this equation is the shortest possible curve, and every shortest possible curve always exists and satisfies this equation. But I can't say that just yet. I have some theory still to do. But let me make a definition. Let me say that any curve there is which satisfies this equation, let me call that a geodesic. So any curve whose curvature is normal to the surface is a geodesic. And this, of course, includes shortest curves if they exist, but it's possible that there might be other curves out there that satisfy this equation. We don't know. Okay? But the definition is any curve whose curvature is orthogonal to the surface is going to be called a geodesic. Okay? Step one. All right, make sense? Okay, so now I can move on. Yeah, so I guess I should say, what's the goal of the next couple of slides? The goal is to prove that the geodesic equation, which I just wrote down, so that guy, that geodesic equation uniquely characterizes, well, up to a small interesting ambiguity you can understand, characterizes shortest length paths. So, in other words, if a curve is a geodesic, then it minimizes length, and if it minimizes length, then it's a geodesic. I want to make that connection. So to do that, I need a bunch of machinery, unfortunately. And I think, again, a lot of this is going to go into a supplement for you to read carefully in your own time, and you can ask me questions about it later. Because I think it just would be hard for it to come across in a quick lecture. Okay, so what we're going to see later, right, so how do we start? Let's start the theory of geodesics. So the first thing we do is we think about that equation. Okay, so that equation, I'm going to show you on Monday's lecture that this equation is a second order ordinary differential equation. It's an ODE, in fact, a system of ODEs for the curve. Okay, it's a second order ODE. That means it needs two initial conditions. Right? An ODE needs initial conditions, and the second order ODE needs two of them. The initial position and the initial direction. Okay? So what you say, what we're going to find is that if you prescribe a point P and a vector x, then there exists a unique geodesic. This is gamma of t in arc length. Such that gamma of 0 equals to, well, not arc length, sorry, just gamma of t. Gamma of 0 is equal to p, and gamma dot of 0 is equal to x. So solving the ODE means taking the initial data and integrating forward in time, integrating the ODE forward in time to get the curve. And the curve is the geodesic which solves the ODE. And I say it's a local solution because, as always, you don't know if the Euler's method you use or whatever is going to converge necessarily as you make t larger. So you can always integrate forward for a little bit of time. You can't necessarily always integrate forever forward in time. Your question?
The endpoint isn't treated as an initial condition?
Not in this case. It's much harder to solve ODEs when you fix two different endpoints. The theorems are much cleaner, and when you give initial data at one point only. Yeah. There is a separate theorem, but you do prove the existence of this later. But it's a deeper, more complicated theorem. It's called the Hopf-Rinow theorem. I'll state it in the lecture. Okay. So now that we have forward-moving local solutions starting at an initial point, I make a definition. I'm going to call this mapping which goes from point and vector to solution. I'm going to call it the geodesic flow. That's one way of doing it. Or another way of saying is it's the exponential map. So the geodesic exponential map takes you from perhaps short vectors, because you can't go that far necessarily, at a point. It is the mapping which takes a vector at a point and moves you forward along the geodesic starting at that point. So that's best explained in the picture. So XP looks like this. Here's my surface, right? Here's my S. And over here is a point P, and then here's the tangent plane at P. Tangent plane of surface S. And here's a vector X. And what X does, what the exponential map does, is it asks you to move a distance 1 forward in time, or forward in length on the geodesic, in arc length on the geodesic. So what you do is you start at P and X, and you solve the differential equation until you've solved for 1 unit of time. And you end up over here. This is X sub P of X. So X, as a result, is a mapping from the tangent plane of the surface into the surface itself. So my M should be an S over there, pardon me. M is manifold, S is surface. Okay, so the exponential map maps you forward. It's justified by the existence of ODE, the existence of solutions of ODEs, right? You start at P and X, you integrate forward in time the ODE until you get to where you want to, until you've gone a unit distance, and then you're at the point X, P of X, the vector X. And of course, the geodesic itself, the whole geodesic, sort of as you go from here to the end, well, you write it like, you can prove that this is a bit of work that goes into that. But in any case, as T varies, T in 0 epsilon, you get this, well, let's say 0, 1. And of course, you make X short. Yeah, so, right, so if you're moving along the geodesic, you're moving along a distance T. So if you've got a distance T outwards, because T is proportional to the distance, never mind the details on that. But in any case, T is the parameter which moves you at constant speed forward along the geodesic and lands you at X, P of X at the end and starts off at P at the beginning. Okay? So this is a picture of the exponential map. Yeah, so the exponential map is a way of mapping the tangent at a point onto the surface by means of walking forward onto these geodesics. This is the important tool that we need for this sort of local analysis of geodesics. Okay, make sense? Yeah?
So wait, when you said 1 unit of arc length, do you integrate over 1 unit of time going forward, or are you waiting until you hit 1 unit of distance going over the surface?
Okay, it's a good question. Yeah, so I'm sort of, yeah, you've picked at the thread which didn't explain so well. Okay, so the fact of the matter is, geodesics are parameterized not by arc length, but they're proportional to arc length. So they're constant speed geodesics, but I haven't given you the speed. So I get a choice of scaling the amount of time that I travel on the surface, or scaling the length of the surface, and they're inversely proportional to each other. Right? So what I've decided to do is make X a very short vector, which means the speed is very small, but I move for 1 unit in time. So in the end, I've only gone a short distance. But I could do it the other way around. I could have X to be a unit vector and T to be a short amount of time. But in any case, so that they're coupled, right?
Okay.
You see? Yeah. Okay, I didn't explain that so well. But in case, I want to keep t between 0 and 1, and I want to make the x vectors as short as necessary for it all to be well defined. Yeah?
So is the goal here to only define the geodesic in a small local region, or be able to parameterize it so you can extend it as long as you need?
Well, it would be nice to extend, so you want to extend it as far as you can. But the existence and uniqueness theorem of ODEs can break down. So you don't know how far you can go. So let's just say epsilon, or not epsilon, I guess, the length of the vectors that you choose. Make them as big as you possibly can before things go wrong. And there are cases, like for example, when M is a compact manifold, or M is a compact surface, where the domain of the exponential map is the whole thing. So you can actually define the exponential map on the whole surface, on the whole tangent plane. But you can't always do that. So I'm just leaving it up in the air so that we don't have to make a decision. Okay, so this is the tool, is the exponential map. Now, what I would like to prove, and in fact, I'm going to put this into a supplement, I think. What I'm going to prove, what you can prove using this tool, is that geodesics locally minimize length. Yes, we'll see. I'll definitely put it in a supplement. I'll probably talk through it a little bit at the beginning of Monday's class. So maybe if you just read it before Monday's class, it may walk me through there a bit easier. Okay, so so let's look at the theorem. The theorem that we're going to prove, or that I want to be able to prove, is that the geodesic equation characterizes locally minimizing curves, length minimizing curves. It's not necessarily going to be true about the whole surface. We'll talk about that in a minute. But I want to say that if my curve is sufficiently small and it's a geodesic, then it minimizes length. So how do you prove that? Well, so how do you phrase that? Prove it. How do you phrase that? Well, I want to say, if gamma is a sufficiently small geodesic, and C is a curve that has the same endpoints as gamma, then the length of gamma has to be shorter than the length of C, which means gamma is always the minimizing length object. And the only time you ever get equality is if gamma and C are in fact the same curve. So the picture of the theorem is this. Here's my big surface, and here's P, here's Q, and here's my geodesic gamma, right? So P and Q are somewhere in the surface, but they're sufficiently close together because this theorem is only valid for sufficiently short geodesics. And here is a different curve. Here's C, and what you have is that length of gamma is always the smaller of any other choice of curve C that touches the same endpoints. Okay, so let me not prove the theorem. I'm not going to talk about the theorem because I'm running out of time. So let me go to the end of my lecture. I'll put this in a supplement. You can read it, and then we'll discuss it in about 10 minutes or so at the beginning of next Monday's class. Okay, so the theorem that we prove using the exponential map and the existence of local geodesics is that geodesics locally minimize length. Okay, so this is my last slide, I believe, yes. So this brings us, once we have the geodesics locally minimize length, we have enough to talk about global properties of geodesics. So it's going to culminate in this Hopf-Rinow theorem. Okay, so what do we know so far? We know that, so I'm at the top there, 3 bullets on top. What we know about geodesics so far is that length minimizing curves, if they exist, have to be geodesics, because that's how we started this whole topic. We also know from this theorem here that short geodesics are length minimizing. We can also cook up, so another thing we have to point out, sort of fact here about long geodesics. So a fact about long geodesics is a long geodesic isn't necessarily length minimizing. Okay, here's a sphere. Simple example is provided by the sphere. It's true on other manifolds too, other surfaces too. Let's take a point P. Let's take a point Q1. There's a unique length minimizing geodesic. The There's a unique length minimizing geodesic connecting from P to Q1. It's called the Great Circle, right? Because you get the Great Circle by intersecting the sphere with a plane that goes to the origin. It's the curves along which airplanes are supposed to fly to get from P to Q1, right? Okay, let's start moving this point. Let's go further along the Great Circle. The geodesic here's Q2. Still length minimizing, still unique. There's only one way to get from here to here in a length minimizing way. Let's get to the north, now we get to the South Pole. So this is P is equal to the North Pole, right? Okay, how many length minimizing geodesics are there between P and Q3? Infinitely many curves, right? They're all length minimizing geodesics. So there's more than one length minimizing geodesic connecting P and Q. Another phenomenon which we can just point out already using Q1, we can revisit. Let's revisit Q1. How many geodesics, now that we see this picture, how many geodesics connect to Q1? There's in fact two of them. Yeah, exactly right. There's the blue one. There's this geodesic here. This is the unique length minimizing geodesic. But then there's another geodesic which goes around behind the sphere. This is a non-minimizing geodesic. Okay, so you have more than one geodesic, and only one of them is length minimizing. Okay, this is a bit problematic when it comes to global geometry of geodesics, but never mind, you have to deal with this, so we do. Okay, so next thing you do is you turn the surface S into a metric space. So you say the distance between 2 points is just the infimum of the length, it's the length of the shortest possible curve. And it would be nice, and you can prove easily enough that D is continuous, and it's easy enough to show that D satisfies the triangle inequality. So the surface S is a metric space in the sense that there's a way of measuring lengths that satisfies the triangle inequality and is continuous. Okay, now it would be nice if the length minimizing curves were always geodesics, and not something weirder somehow. And there should always exist a geodesic. Anyway, the Hopf-Rinow theorem is the final piece in the picture. It says that, so first of all, there's a local condition, which is the exponential map, if that's well defined everywhere, and defined, and you can continue geodesics always, and the neighborhood on which it's defined isn't local, but it's the whole tangent plane. So if X is a globally defined object, then any 2 points can be connected by a geodesic. And in fact, by a minimizing geodesic whose length is equal to the distance between those 2 points. So the Hopf-Rinow theorem completes the picture. It says that any 2 points can be connected by a length minimizing geodesic, provided that the X map is well defined, meaning provided that the process of solving the ODE is reasonable. Okay, so we're done. Let me just go back one slide and then we're really done. So in order to prove this, I have to go from local to global, and that requires some technical arguments, which I haven't had time to do today. I'll write them up and you can read them, and then we'll walk through them on Monday. Okay, thank you very much. See you guys on Wednesday.